So picture this. You've built a high-performance trading bot. In all your tests, it's lightning fast, executing orders in just a couple of milliseconds. But then it goes to production, and right when things get crazy, it just chokes. Orders are late, connections are dropping, and no one has a clue why. Okay, let's dive into this technical whodunit and uncover the hidden cause of a really nasty production failure.
And this, right here, is the paradox that was driving the engineers absolutely bonkers. Every single line of code on its own worked perfectly. The logic was totally sound. But when it came to timing, which in trading is literally everything, the system was a complete mess. It was doing all the right things, just at the absolute worst possible time.
So let's get specific on the problem they were seeing. They had a critical trade setup with a simple 10-millisecond timeout. The expectation, obviously, is that it fires in about 10 milliseconds. But the reality, it was firing hundreds of milliseconds late, sometimes even half a second late. You know, in the world of high-frequency trading, that isn't just a delay, that's an eternity. That's the difference between making a profit and taking a massive loss.
Okay, let's look at the crime scene, because it's a really weird one. You've got these huge delays, you've got keep-alive signals timing out, but all the usual suspects have a perfect alibi. I mean, look at these metrics. The CPU is barely breaking a sweat at 40%. Memory is totally stable. The network is blazing fast. The system is grinding to a halt, but not for any of the reasons you'd expect. This was the exact question that was haunting the entire team. It was like they were hunting a ghost in the machine. They'd built a system that was failing silently, without leaving behind any of the usual fingerprints. So what on earth could be causing a perfectly healthy system to become so, well, temporally broken?
And here it is. This is the first major breakthrough in the case. The team's entire mental model of how Node.js actually works was just wrong. See, they pictured the event loop like a nice orderly line at the bank. First in, first out, where everyone gets their turn. But that is not how it works. Not even close. The reality is way more complicated, and that fundamental misunderstanding was the root cause of this whole mess.
And this leads us directly to the name of the culprit we've been hunting for. This hidden gremlin has a name, and it's a term that every single Node.js developer really needs to burn into their memory: phase starvation.
So what even is phase starvation? Well, it's not one big slow task blocking everything up. It's actually the complete opposite. It's when you get this relentless flood of tiny, super fast tasks that all pile up in one specific part of the event loop. That one little part gets so overwhelmed that the event loop literally gets stuck there and it can't move on to do other critical work, like, say, processing our timers.
To really understand how this happens, we need to pop the hood. We've got to do a quick dissection of the Node.js Event Loop and see how it actually works inside.
So, the most important thing to get is that the event loop isn't just one big to-do list. It's a sequence of distinct phases, and each one has its own little queue. First, it runs the timers phase for things like setTimeout. Then it moves on to the poll phase. This is the real workhorse, where all your network and file I/O callbacks get handled. And after that, you've got the check phase for setImmediate. But there's a wild card here, a secret player called Microtasks. These are things like your promise handlers, the .then blocks. And here's the kicker. They aren't a phase. They're a special, super high priority queue that gets to cut in line. Whenever a microtask gets created, it runs almost immediately, before the event loop even considers moving to the next phase.
And this, right here, is the murder weapon. Microtasks don't wait their turn. They completely disrupt the normal, orderly flow. So back in our trading bot, you had thousands of I/O callbacks firing in the poll phase. Each one resolved a promise, which created a microtask. The event loop got trapped in this vicious cycle, bouncing between the poll queue and the microtask queue, over and over, never getting a chance to loop back around to the timers.
Now, this is what a healthy, happy system looks like. See how the work is spread out? The event loop spends a little time in each phase, everything is balanced, everything is moving along smoothly. This is the dream. Your tasks run predictably. And now, look at this. This is our system during the failure. The poll phase has become an absolute monster. It's just gorging itself on all that incoming market data and the thousands of micro-tasks it creates, and it's monopolizing all the runtime. And our poor little timers phase, where our critical trade logic is sitting, it's completely starved, just waiting for a turn that never comes. So this specific failure actually points to a much bigger, much more fundamental trade-off in how we design systems. It's this constant battle between two goals that are often at odds with each other: maximizing throughput versus ensuring predictable latency. And this really lays out the conflict perfectly. You see, Node.js is by its very nature optimized for throughput. It's designed to handle a massive number of requests per second, which makes it amazing for web servers. But the very thing that makes it great at that, batching all that I/O in the poll phase, is exactly what makes it hostile to predictable latency, which is non-negotiable for something like a trading bot.
Now, a lot of developers, when they run into something like this, their first instinct is to try a little hack, like using setTimeout with a 0 millisecond delay to try and yield back to the event loop. But this quote here just nails why that's such a bad idea. It doesn't solve anything. All you're doing is taking your critical task and shoving it into the timers phase, the very part of the system that's already being starved to death.
Okay, so we've diagnosed the problem pretty thoroughly, but how do we actually fix it? Well, this means we have to shift our thinking away from just writing code and towards designing systems that are genuinely resilient to this kind of problem. The most solid solution here isn't a code fix. It's an architectural one. It's called workload partitioning. The idea is simple. Don't mix your different kinds of work. You create one process whose only job is to drink from the fire hose of market data. Then you have a totally separate, protected process that does nothing but your time-sensitive logic. They can talk to each other, but that I/O flood can never, ever starve your critical timers.
And how do you catch this before your whole system melts down? You have to monitor for it proactively. But standard event loop lag metrics aren't good enough. You need to specifically measure timer drift. That's the gap between when a timer should have run and when it actually did. If you see that drift getting bigger as your traffic goes up, that's your smoking gun. You've got a phase starvation problem.
This is a classic example of what's known as the noisy neighbor problem, and it can happen inside a single application. So imagine you've got a simple log shipping library. That's your noisy neighbor, and it starts flushing a bunch of data to disk, flooding the poll phase with I/O. The victim? A tiny little heartbeat check running in the timer phase, whose only job is to tell the load balancer, hey, I'm still alive. But because the logger starves the heartbeat, the load balancer never gets the signal, assumes the service is dead, and kills a perfectly healthy process.
Which really leaves us with this final critical thought. It is not enough for your application to just be busy. It has to be busy in a balanced, healthy way. So I want you to go look at your own systems and ask yourself this question. Is all that activity, all that busyness, actually a good thing, or is it silently suffocating the tasks that matter most?